Good morning, and thank you very much for a very nice introduction. I don't think I deserve many of these things because most of the work has been done by people other than me. But yes, I have been associated with most of it, and some of it I will share with you today. And also, I will take you with a little bit of journey into what is textile. So it's one of the most misunderstood word in today's technology. We all know textile as we wear it, but we don't know what textile is capable of doing and where it is capable of taking us to. So I'll try to give a little glimpse of that based on the kind of work which we do at the department, and especially in the lab and the group which we have created, which is called Smart Materials and Innovative Textile Application. So I'll begin with this, and I'd like to also thank the organizers of Bangalore India Nano for inviting me and giving me this opportunity to share my thoughts and my work with you. And thank you for coming and listening to me. So, as I said, most of the work which I'm going to present today relates to this lab, which is Smart Materials and Innovative Textile Applications Research Lab. I would tell you that this is now a registered trademark of IIT Delhi, this lab, this symbol, everything. IIT Delhi now owns it. We started working in the year 2000 with a very small group, and today we have a state-of-the-art research lab in IIT Delhi with funding from industry and DST. And a significant amount of money has come from industry, which is a very unlikely thing in India usually seen. At a time in 2007 when we established it, we had very good participation from Indian industry in this. This is a research group right now I'm coordinating, and you can look at our activities at smita-itd.com. This is a website which we have. These are the major research areas which we have been associated with. One is responsive textiles, which responds to the environment. It can be heat or chemical storage in a reversible manner. It can be a shape change, one way, or reversible for robotic kind of applications. Then, obviously, I'm not going to talk about this area. Today, our emphasis is mostly into nano, and nanomaterials and textile, and what that can do, and how we have been using it. So whether it's nanofibers, whether it is applications in filters or responsive composites or tissue engineering, we are doing a lot of work with All India Institute of Medical Sciences in New Delhi. And then nano finishes, some of it I will share. We are also working on atmospheric pressure glow plasma and using it for creating nanostructures on textiles and having many functionalities in a very eco-friendly manner, and then specialty materials and fibers. So today I'm going to talk a little bit about the specialty fibers and materials, as well as something on nano, which we had done in the past. So what is and why nanotechnology textile? Why should we even worried about it? Well, Indian economy, as you know, is growing quite fast, and it is expected to touch $5 trillion in 2025. And textile makes a very big impact or very big contribution in this. Why? Because textile industry is actually next to the agriculture industry in India. And that employs a whole lot of people. And a lot of livelihood is dependent on this technology, while it is also one of the most polluting technology in this country. And that is why the industry has moved from west to this part of the world, and now it is moving away from this also. And now there is a challenge that how can we survive and contribute and advance this industry in India without actually creating pollution? And the answer is technical or functional textiles. So we have to move away from traditional materials which anyone can produce to something which only few people can produce. So we feel, and even the government of India today feels, that textile is one of the major contributors of our economy, and we must look at it in a wider perspective. When we come to smart and innovative textile technologies, worldwide it is being now taking a center stage, whether we talk about US, Europe, Australia, Japan. People have now realized the importance of textile materials in today's technology. And there are very large programs. There's recently a launch program which is called Advanced Fabrics of America, which is coordinated by MIT, where almost 340 institutions and industries have come together for a very large funding to create textiles of next generation. it is said that almost $5 billion industry is going to be created in the next 2 to 3 years with a very high rate of growth. And technical textiles, functional textiles, and smart intelligent textiles is going to be the framework for that. So I'll begin from something like this because this is, as I said, one of the very misunderstood word, but also not probably recognized well by people. What does it mean? What is textile? Is it just what we wear or what we see, as I said? Actually, obviously, it is what we wear and what we see, but at the base of it, there's something called fibers, okay? So it's an engineering of fibers in a manner. It's a, there are two categories, fibers and filaments. Fibers are short and filaments are very, very long, and can be infinitely long. And they're essentially a one-dimensional structure. So textile is nothing but engineering of one-dimensional structures, one-dimensional structures taken together into either two dimension. So these are, for example, it's a micrograph of a cotton fiber, as you see it under a scanning electron microscope. And you can turn them into either 1D structures or 2D structures or 3D structures, which are of various kinds and for various applications. So really, it is the engineering of these fibers. And why? What is so special about this fiber? Well, it's a very unique material. Now, you people are all material scientists, I would say, and trying to deal with all kinds of materials, whether it's a physical or something. Let me compare only two kinds with what textile has. If you look at metals, which is very well known and very widely used, and you look at just two properties as of now, say modulus of four kinds of moduli and strength. So what we see is metals are mostly very high in all these values. So they are quite stiff. When we say modulus or moduli are very high, they're very stiff. And when we say strength is high, obviously, tensile strength or compressive, etc., etc. If you go to the civil materials, which are concrete, bricks, and composites of these, then again the moduli are very high, but their all other strengths are very low except for compression strength. Compression strength is obviously very high because you can build very, very high towers. But when we come to a textile material, it's a different set of properties altogether. All the moduli are extremely low. They're so low that it's very difficult to measure them also, while strength-wise it is very, very high. And only one part, which is compressive strength, is not that great, but other all strengths are quite good. So that makes a unique material. And now if you compare strength-wise with other engineering materials, see the highest strength metallic fiber which you can create in today's industry is a piano wire, which has a strength of about 2500 megapascal. And if you look at the textile fibers, they easily cross. The normal fibers cross the normal steel wire, but the high strength fibers which we have in our industry can cross all these piano wires by any margin. So what is so unique about this material? One, obviously, is moduli. What is there? What else is there? So it's a fundamental unit, as I said, of the textile material. I said it is one dimensional, that I already told you. I also told you it's very flexible and very strong. One of the most interesting property other than these is the extension and recovery. See, if you look at metals or other materials or ceramics, they hardly extend. And the extension will be at the order of 0.4%, 0.2%. Here we can extend the material to 30 to 40% and still recover most of it. If we extend by 10%, then it will recover almost nearly 99, 95%. If we extend it to 40%, it will recover almost to 80%. So this is the kind of recovery. That is why we wear it and our dresses do not get deformed, whatever we do with that. So it's a very unique material and requires an engineering of its own. And this is very different from a plastic material, though all the fibers are made from polymers, but plastics and fiber are totally two different things because they have extremely different properties. So textiles can be used in structural applications. This is already being done. And this is where now Government of India and our country is now driving, which is technical textiles. We can create civil structures, embankments, and pond linings for various kind of things. So it has been recognized now that textile can be used to save cost of our development. Why? Because if you use textile materials at the base of highways, roadways, and railroads, then the life just goes by many folds. So you don't have to repair them, you don't have to rebuild them. Initial cost may be a little higher, but then the life is much longer. So there's a considerable cost saving. There's a considerable energy saving. If you have to talk about mobility, then without textile fibers, mobility is absolutely unthinkable proposition because you have to reduce the weight. And the only way you can reduce the weight is by composites. And the heart of composites are fiber. So whether it's carbon fiber or other high tenacity fibers, you have to create them in the way that it can reduce the weight of your automobiles or your transport materials. Today, even aircraft industry is looking at replacing aluminum hybrids by carbon fibers and other kind of hybrids because weight is every 1 kilogram, if you reduce, you can really save 35,000 liters of fuel over a life of a plane. So it's a very important aspect. The other thing where the world is moving is toward energy harvesting and then sensing. And textile is one thing which is on our body all the time. So it can fulfill certain needs as well as if we can create and put it in various kinds of scenarios and buildings and in a very flexible manner, then obviously energy harvesting becomes very interesting. Otherwise, silicon, etc., are very rigid structures, and that is the problem with it. The other important area is health, rehabilitation, and implants, which is again a very important sector for a country like us, where a lot of people require a lot of help in medical ways. And the conservation of water resources, as I said, pond lining. If you don't want water to percolate below that, textile is the answer for it. Let me come to the interest of this audience, which is nanotechnology. So what is nanotechnology doing for textiles? It's actually taking the textile to the next generation and has the capacity, as in any other area, which you have heard in this conference and will be hearing. A lot of interesting devices have been made, a lot of small layered, single layered 2D structures have been created. This is a totally different way. We are not really interested in those kind of minor things, though that can also be utilized. We are looking at how these materials can change the whole functionality of textile in a very different manner. So we are not talking about micro or nanograms of material being processed. We are looking at even kilograms of material being processed. So one of the challenges in textile and nanotechnology in textile is that we have to upscale it in a really big manner. Some of the nano initiatives which are being taken is nanofibers. You are aware of it. So, but most importantly, we have to work about the nano spinning or electrospinning of on biomaterials. This is one of the most challenging areas, and we have been doing quite basic and fundamental work into how the processing can be improved and taking the diameters as low as possible. For people who are physicists in this audience, obviously 100 nanometer will not be called nano from any angle. So you are talking about 1 or 2 or 3 or 4 nanometers. But we are here talking about bringing the dimensions down to create something which is interesting. So in a broad definition, anything which is less than 100 nanometers is considered to be nano for these applications. Similarly, whether we talk about nano surfaces, modifications, using atmospheric blue plasma, that is, I said, is again a nano initiative. Nano finishes is one of the initiatives where we can put nanoparticles right onto the textile or inside the textile to create various functionalities, and then nano composite fibers, which I will throw some light today. So some of the, initially I will tell you some past work which we had done and where some success has happened in commercializing this nanotechnology, because that is one of the most important things. If we are spending money in research, we need to take it to the general public as well. How do we do that? Well, one of the very simple things which you must have heard in the literature many, many times, we can create antimicrobial materials, we can create self-cleaning materials, super hydrophobic. Things are known. I mean, you can find probably 1,000 papers in the literature. But has any of these things really gone into commercial area? No, because there are huge number of problems. The problem is stability, problem of attachment, they're leaching, creating it in larger quantities, applying them, storing it, stability for very, very long time, transportation, mixing it with all kinds of chemicals while being application. There are 100 challenges before any of these technologies can actually see the day of light. And we have been, I will give you one example of silver. Now, silver is one area which is very well known. Nano silver, I think probably any group in the world must have worked on it. So what is so new or interesting about it? But we created something very interesting. We created something which is called now, known as N9 technology. It's called pure silver technology. It's blue in color. And it has certain advantages, which I will come to you. This technology was created in association with Razel, which is a Bangalore-based company. You may know, many of you. And ARCI was also partner to it in this project, larger project. But this N9 silver technology was created at IIT Delhi. It's a unique product. It's a nanotechnology. It's a nanomaterial, which is in the range of almost 2 to 3 nanometers and still have a color of blue. Normally in literature, you will find the blue colors associated with prism kind of structures, which are of 30 to 40 or 50 nanometers. This is a non-yellowing. So silver, if you take to nano, mostly it will create a deep yellow or a brown color, which you cannot apply on a textile material. Who will wear a brown shirt or have shirt with less whiteness than before? So we had to have something which was very effective and yet not non-yellowing. So it's a non-yellowing. We wanted something which is highly stable. This dispersion of nano blue silver is stable for over 2 years. We have tested for 2 years. Still, we have stocks lying in our lab which have not degraded in any manner. While it is known that all kinds of non-circular nano materials, they degrade with time with light because of the reactions associated. But this has not. It's very high color stability, very high antimicrobial effect. Actually, the MBC value is the lowest reported in the literature. It's less than 0.05. And if you look at all the other literature, there's nothing reported less than 5 ppm. So we are talking about 2 orders of magnitude lower concentrations, as effective as any other silver product in the market, anywhere in the world. And that made this technology extremely successful, and all the multinationals could not stand in front of it. Then obviously safety is another concern when we talk about nanotechnology, how safe it is to human body, and when we are putting it on textile, we have to very sure it is coming in contact next to the skin. And it will get absorbed through the skin and can create a lot of problems. And there are obviously very high standards for making safety. Before it can be put by a textile industry on a material, on any textile surface, it has to go through several tests. People who are biologists, microbiologists may understand these tests better than me. Very expensive, very long tests, and this material actually passed all of them with flying colors. Silver, as I said, so many patents, so much literature, we could still find a place for it for patenting. And today we have got granted patents in many of the major countries where this product is now being sold. So it is right now launched in almost 9 countries, different countries of the world. And it has over 200 brands which is using it. And you can, if you look at the brand list, probably will not find a brand, international brand, which is not there on this chart. That shows the power of nanotechnology in textile and what it can do to the industry of India if you can create the right properties in a right manner and bring it to the world. I'll give you some of the photographs. This is Wrangler. You go to Wrangler stores anywhere in the country, you'll find all the jeans being treated by that. They won several awards because of this, the company. I would say most of the work on application has been done by the company, and they deserve all the applaud for it. IIT Delhi is associated only for creating it to the bench level. Taking it to the commercial level and launching it, obviously, is the hand-holding done by the industry, and they have to be part of it. So whether, and very recently, all the FIFA T-shirts in Dubai, the international match, they're all treated with this product. So you can look at, I'll just go through them very fast. So various kinds of textiles which we can use and the technologies. And this is interesting. So why only textile? This material can go into now plastics. It can go as a hand wash, which is an alcohol-free hand wash. So they have expanded the applications now into various domains which were not seen, whether it's a car maintenance or whether it's an airport. So if you go to your Bangalore International Airport, this product you'll find. Or whether it's a plastic tank on the roof of your house. So this is how the silver technology, which was meant only for application on a textile T-shirt or a shirt, has now gone into various aspects of it, and it was recognized by the government of India, and we won the 2016 award for it. Another example, nanofibers. Again, we all work on nanofibers, but when we talk about application of nanofibers, every industry shucks away because the cost is very high. You need them in large quantities. There are companies which have machines, created machines to make nanofibers, but still commercial applications are not there. Why? Again, it's a stability of nanofiber, whether on a substrate, its adherence, which does not stay on it very long. How much is effective? What is the cost of production and applying it? These are the questions which have to be answered. So we thought of something, we thought of creating something to tackle with the pollution. We know Delhi is probably the worst of all. Bangalore is only half good. But we can look at, obviously there are industries and there are all kinds of situations. Really, these are the hazardous conditions in which our people work. So we thought of creating something for the general population using this technology. So whether they're working in a hazardous industry or on road or in traffic as a traffic police person or school children and dealing with all these kinds of pollutants which you are aware of, we thought of creating a mask. Now what is so interesting in it? Masks are available. 3M sells a mask like this, not on nanofibers but other technologies. And there are nanotechnology based products also in the market. But if you buy them, they will cover your half the face. And they're very expensive also. Why? Because when you filter something so precise, your pressure drops are very high. So you have to create a larger surface area for you to breathe with the kind of pressure drops your lungs can create. We thought of, and obviously people have been working on it, trying to make it smaller, and these are some of the products which are there in the market based on various technologies and coming to nose inserts. And we thought of really creating something on the nasal. So you can stick it like a Band-Aid on your nostrils. So the area is now 1/10 or maybe even smaller than a mask. And you have to have the same pressure drop and the nearly same kind of efficiency. This is a challenge. How do you do that? And still should be stable to manufacturing processes, stable to handling, stable to distribution, and so on and so forth. And we eventually could create something. So there were 3 students, our ex-students, recently graduated, who came to us, who created a company. These 3 are the people. Some alumnus who wanted to fund this project, and we went ahead and made something called nasofilters. And nasofilters has a shape like this, and you can see this kind of area is very, very small. Concept is very simple. Concept is HEPA filter, you have large fibers, you have to create a small opening to trap these fibers, these particles. If you can keep on making the diameter smaller and smaller, you can do the same kind of filtration, but much better, much lesser pressure drop. So resistance keeps on going down. So idea is to create fibers which are as thin as possible. Not only that, these fibers can actually fly into your nostrils. They may get caught, but they may also get settled in your lungs. So they have to be biocompatible, bioabsorbable. They should be biodegradable. People should be able to throw this anywhere, and we should not be worried about creating another problem. So that means you have to create fibers which are biomaterial-based fibers, which can actually be put in a very stable manner on another textile substrate, and create something which is usable over a period of 8 to 10 hours in a day. And we've seen how it captures different particles, and it's a very efficient manner, and this product is now available on Amazon, as well as you can go to our website and buy these things. Very cheap. 10 rupees, 1 piece for 1 day of use. This is how to bring it to the masses. So if you have to bring the technology to masses, we have to think of these kind of applications. And the amount of nanofiber we are putting there is very, very small. So that becomes very cost effective. Obviously, the process of putting those are where the whole interesting technology is. So you can hardly see it from a distance, whether it is being worn. And we won a startup award last year. And this company also was selected among the top 25 companies by Grand Challenge South Korea, where almost 500 companies from world over competed. And this company was given a startup space in South Korea and collaborate with the South Korean companies to work on it. Let me come to these are successes which has happened. Let me come to what are the new directions which we are taking and where textile can go. You have to still talk about high performance materials. I told you we have very high performance, high strength materials, but we cannot, they're very expensive. Most of them are imported. No country wants to put a manufacturing plant in it. There's a serious issue whether how we can create other fibers in our own country which are suitable for some of these applications where carbons and Kevlars and Nomexes can be used. So can we use nanotechnology to do something like that? I'll show you one example. Conducting fibers, supercapacitive fibers, infrared reflective fibers. You can think about anything where flexibility, strength, and usage in any condition textile comes to the mind. So we are thinking of doing all these things, which you do on semiconductors, on silicons and glasses and things like that. We're trying to create not textile as a substrate, but textile as a material. So there's a difference. So we created one example. We created some nanomaterials. We synthesize everything from scratch, whether it is available from literature or not, because we need to have them in the right manner, in the right quantity, as well as right dimensions. So we created particles, rods, wires of ZNO, and we added them into the fibers inside a textile fiber. And we saw that the material characteristic, the crystal structure of the fiber itself changed dramatically. Something where we had a gamma phase more in nylon and alpha less. If you add a particle, even gamma becomes more. But when you keep on increasing the dimensions of these nanomaterials, the whole story reverses. And reverses not at the rods that much, but at wires, it is absolutely a different story. And when you have an alpha structure of nylon created, the strength just shoots up like anything. So, and then obviously when we spin fiber, then we have to draw it, we have to heat set it, there are several steps involved, and we see that this ratio of alpha to gamma keeps on increasing very, very fast, very, very high, while other materials which are, or other traditional materials which are there, nothing happens. We saw that these fibers, when these structures, when we put in a polymer matrix, polymer really interacts with it. Obviously, it's not that you put this material in any polymer and it will happen. You have to look at the interaction, the surface interaction, and how they bond with each other, how they like each other. And that is obviously, you have to do a lot of studies, either Raman or other characterizations, to see what kind of groups can be created and what kind of compatibility they have. And once you can create those things, what we see is as we increase, these are 3 aspect ratios, ZNO particles, I don't think you can see this curve, but it lies, these points are there. And then ZNO rods, and then this is ZNO wires. And we can add them in very, very small quantities, 0.5% to 1%, 1.5%. Actually, if we can do really very good mixing, we can probably go less than 0.5%, but we all know nanomaterials are very difficult to disperse and separate once created. So, but we still do. So all the technology here is on dispersion, how to disperse them. And we see that the properties of birefringence. Birefringence is the orientation. So fiber is nothing but polymer chains oriented in one direction preferentially. So this orientation, this preference of orientation keeps on getting higher and higher as we add these materials of high aspect ratios. So what does it do? Nothing happens at the crystalline front. There the orientation remains what it was. But the amorphous region of the fiber just gets up and gets oriented and stays oriented. So this shows that polymer chains are interacting, and it is actually the amorphous phase also acting like a semi-crystalline kind of a structure which is more stable. And that brings the change in the properties. And if you look at the morphology, this is a normal nylon fiber. And as you add on material, the morphology starts to change into more fibrous. So fibril, we call it fibril morphology, where the chains are now into bunches and coming together to create fibril structures. And you can really see as if a fiber has fibers inside it. And this is how nature does it actually. Nature creates cotton and other kinds of fibers just like bundles of chains put as fibers, and we call them fibers. And we are not able to do that using our technologies. But now Nano can, to some extent, do this kind of a work. And what happens to the properties? This is a tensile property. For a normal nylon 6, it's a commodity material which we wear. If you put particles, not much increase, and most of the literature is filled with this. We add nanomaterials, nothing happens, 10% increase, sometimes lower than that, less than the original values. You go to rods, there's a significant increase. You go to wires, there's an absolutely phenomenal change in the strength. Just don't pay attention to the strength. Look at it, the extension, how much this fiber can be extended. We have not sacrificed much on the extension. And if you look at all other high performance fibers, if you put anything, if you orient them, if you put a rigid structure in them, they gain strength, but they lose extensibility. Carbon fiber, Kevlar fiber, they have very low extensibilities. That is why they have to put in a matrix to do any impact kind of work. But here we are not losing on the extensibility. And that brings us near to the spider silk. We all know spider silk, drag silk line of spider has a very high impact strength, one of the highest reported, 165 joules per gram. And we have actually achieved that with this fiber by adding only 1% of nanomaterial, which is structured right and blended in a manner that it works with it. And what we feel with what is happening is, this is a proposed structure. All theories are proposed, and mostly they are wrong, right? So whatever the amorphous areas, these rods probably are going there, these wires are going there, and they are trying to create and make these amorphous bodies, which really deform very easily, stay in their place and create that kind of a properties. We thought about why not put these materials inside a nanofiber. Those are macrofibers. And we could put our ZNO wires and things like that, even silver wires and things like that, right inside the nanofiber. So the strength of nanofiber also goes up significantly. We can't really measure one single fiber, but the bundle of the fibers, we could see the strengths are very, very high. And a lot of other functionalities can be added by doing that. Now I move on to the next part of my talk, and that is on flexible electronics. Now, the heart of flexible electronics, as I understand, I'm not really a right person to speak on it, because you people probably know 100 times what I know. But we are trying, what I understand is that a flexible conducting material is a very essential component of a flexible electronics. Something which is stable, something which can interact. So can we do that? So we have only films, no? Plastic films, which we call very flexible electronics. We say flexible electronics, films comes to our mind. Why films? Why not fibers? Why not clothes? Why not any structure or bundles which a textile can create? So we thought about doing something in that direction. And something came to our mind, polypropylene, polypyrrole. We know polypyrrole, non-processable material, very highly conducting, very stable. You mix it as a particles, nothing happens. The blends are really non-conducting. So we thought of creating nano rods out of polypyrroles. There are literature studies how to create them, and we have successfully created them using certain methods and modifying them. And then came the question whether we can add only 0.01%. Obviously not. We need to add more. So we have to scale it up. Then came the question how to scale up something which is a nanotube, which people make in micrograms, or milligrams. How can you create 30, 40, 50 grams, 100 grams of material in a lab? And we have done that. And these are the materials, these are the rods of polypyrroles. We call them nanotubes of polypyrroles. And these are hollow nanotubes of polypyrroles. So we added them into a fiber. So we created a fiber which is two structures, a core and a sheath. Core had nanotubes of polypyrrole, and the sheath was a normal nylon. We did a bi-component spinning. It's again a very specialized kind of spinning process. And we created a fiber which had a sheath and a core. Core had conducting material, and the sheath was insulating. Then we dissolved the sheath at one end of the fiber. So obviously the conducting surface hopefully has come out. And then we took it as a wire. And what we see is if you do not remove the sheath, it is absolutely insulating. But if we remove that sheath and come to the core, the conductivity is almost 7 orders of magnitude better. We thought of doing something with the silver. Silver nanowires, people disperse it on a film or create it or blend it and things like that. Problem is aberration, problem is they go off, problem is they don't stick very well, they're exposed, so with time they degrade. So we thought of putting them inside the fiber and creating a hollow structure. So we first made beautiful nano silver wires. See, we believe in making things right. So you have to start from the scratch, not buy it from anywhere. Because what you buy may not be appropriate for you. And obviously, it's not just buying and adding. It is making in the right formulation at the right time when they are still not agglomerated. You have to bring it to a mixing stage, which you can do only if you're synthesizing in your lab or in your region. So these were the wires which were almost 50 nanometers in dia and up to 13 microns long. We did a hollow spinning, solution spinning, where the wires were put in an aqueous media and put inside the fiber, and the polymer solution was put outside that, and it was co-spun together into a hollow structure. And this is the kind of hollow structure we created. So there is a skin of polymer, and there is nanowire layer deposited right inside it, and then there's a hollowness. And we could create these diameters of these fibers of various diameters just by simply changing the flow rates of the core fluid in various ways. And obviously, the kind of the concentration of nanowires, we could create various kind of structures. So we created a lot of structures. And then what we saw, if you really go, very thin layer of densely packed nanowires are deposited, and they are not detachable because they have actually got embedded partly into the polymer which is covering it. So it's a very stable kind of a material. And it's not exposed to the environment because it's inside. We did a knot test. The conductivity changed a little, but not much. That means things are good. We did a strain test. So I told you, we don't believe in 1 or 2% extension. We believe in 30, 40, 50. We said 100%. Why not? So 100% extension. And what we saw, obviously, the conductivity is decreasing. Depending on what kind of structure we are creating, conductivity either drops quite a bit or drops by an order of magnitude. But connectivity remains. So is it repeatable? We've cyclized it. 20% extension, again and again, number of cycles, conductivity changes a little. And when we went to 100% extension, again, there is a variation. The resistance goes up, but it comes down, goes up, comes down repeatedly. It cycles very well. Depending on the strain, obviously the resistance changes are there. But stable material, it's a quite stable material. If you just connect an LED, you can see LED glowing at the different intensity just through the fiber. Then the question came, can we do something with it? Can we create a simple device? So we thought, let's create a supercapacitor. So we took a hollow fiber, which we have created. We created another hollow fiber, which is of a smaller kind, and we inserted one into another. Because these are hollow structures. They're very small, okay? They're all 200, 300, 400, 500 microns kind of structures. And then either we filled the annulus with electrolyte or both annulus and core with electrolyte. So this is the device. Then we inserted 2 current collectors, which are just at the end. And so this is a fabricated device. So you looked at cyclic voltammetry, and we found it is having a very high capacity. And if you filled both core and annulus, the capacity went up many times. Is it flexible? Yes, we did a loop test, and nothing much changed. Then, is it stable? Did a lot of cycling? Yes, it does change. But from 100%, the retention, from 100%, it came down to about 70%, and then remains nearly stable. But these are all research devices, so there's no optimization done. They are just made to show a concept. Another area, totally different. So we can create devices, we can create electronic materials and things like that. How all we can do it, obviously, people have to come together of different disciplines to create things which are of order which is totally different. There's another thing which we can do. We thought infrared. See, this is one thing where energy saving is very important because a lot of light comes through, which is infrared, which heats up tents and things like that. So we looked at the range, which is IR range, and we saw that obviously we know heat buildup with the IR as it goes through the textile. Can we do something with it to make it more reflective? So we created molybdenum oxide nanobelts of different sizes. And then we added these, and then we did a very simple test. This is a chamber where this textile has been put, an IR lamp has been put, and we are seeing how the textile temperature changes and how the chamber temperature, which is the enclosed body, how that changes. And what we found, this is a reflection study, that this is your original nylon, 0%, that is the original material, nylon. This is after 1% addition, this is after 1.5% addition. Actually, the reflectivity goes down. So that means it's not working. But actually, no, it is actually working. What is happening is the temperature of the inside chamber has gone down from 72 to 65 degrees in a very long exposure time. But if you look at the temperature of the fabric itself, that has gone up considerably. Which means whatever, it is getting reflected but in a diffused manner and it is getting tracked in the fabric itself. So the fabric temperature is going up while the inside temperature is not going up. So obviously what is happening is very simple, that light rays are getting reflected from these belts which are of high refractive index and of high, and what we found is certain dimensions are very important to do this. So I come to the conclusion of my talk. Very simple conclusion. Textile materials are an important engineering materials. So please do not ignore textile materials. When we think of textile, when we see a word textile, please see it as a very, very important and very advanced material for engineering. And when we see whether nanotechnology can do anything, yes, it can. It has potential to create new fibers with new functionality and novel applications. So thank you very much. I would like to acknowledge Professor Manjeet Jassal, who is very much associated with all these work, my research team and the funding agencies, and thank you for your kind attention.
Since we do not have much time, maybe 2 questions.
As I see, most of the technologies you are using silver. Why not gold? Is there any cost aspect in gold?
Huge difference of cost.
Yeah.
So even silver, people are not using because of the cost, and we could use it because we have brought down the cost by 2 orders of magnitude. Because of our efficiency, as I told you, is almost 2 orders of magnitude higher.
At least to see the outcome of the results, you have tried gold?
No, we have not tried gold. But it would work, definitely.
Thank you.
Yeah.
Sir?
Curious, what is the reason for the blue color? Is it plasmon which you are modifying?
I think it is so. Though I am not really an expert in studying that phenomena, we wanted to, but we could not. Blue color is also, there are various blue colors which we can create. And the size which we saw with small angle X-ray diffraction is so small that we can't really see it in any other microscopy also. So we try to see it, for example, under transmission, we try to see.
This is about 2 nanometers, you say?
2. Average size is 2 to 3 nanometers.
And you don't see a plasmon band?
There's a beautiful plasmon band which is coming out. Why is it coming out? I have no idea. And we don't have large particles. We have very, very few large particles. And the absorption coefficient is very high. It's one of the highest. So it's not that only few particles are giving that kind of plasmon and others are not. It's actually a very high extinction coefficient.
Sir, when you were talking about the IIT blue nano silver, you mentioned something called as the MBC value. What exactly is MBC value and how do you measure it?
Okay, MBC value is minimum bactericidal concentration. That means a given colony of bacteria, what is the minimum concentration required to kill it? So more efficient material will kill it at much lower concentrations.
I think since we are already late, we can interact with it around. So I think let's close the session. Thank you very much.
Thank you.
I would request, sorry for the inconvenience, Professor Ram Gopal Rao, Professor Ashwini Agrawal, kindly come back to the stage, please. No, Professor Ram Gopal Rao and Professor Ashwini. Tata Narsingh Rao garu, koncha wait cheyandi. Please wait for some time. Okay, I would request the chair to give a memento to Professor Ashwini. And also I would request Professor Sood to kindly come over and give a memento to our chair also. All three of you for a photograph, sir. Sir, can you